Right, hello there. This video covers rates and graphs. So we've got the final video in this series of 7. Make sure you've had a look at 1 to 6 beforehand. And I'm going to cover with you how you calculate the rate of reaction from a graph, so how to draw tangents, how to calculate gradients of graphs. So let's have a look, as we've done before, at the reaction of calcium carbonate with dilute hydrochloric acid. So let me just annotate this diagram and do an equation for you. So if you remember, this reaction produces carbon dioxide gas, and carbon dioxide will of course collect in the gas syringe. So what you could do, you could record the volume on the gas syringe, let's say every 30 seconds. So we end up with a graph that looks like this. The rate of reaction will be fastest at the start, and then it will slow down and slow down and slow down until it stops when one of the reactants runs out. So if we had an excess of calcium carbonate, what would happen is the acid would run out and you would see calcium carbonate still left in the conical flask, but there would be no bubbles of carbon dioxide produced. Now the rate of reaction of course changes, and we'd have to work out the gradient of the graph at a particular point to work out the rate of reaction. So what I'm going to do, I'm going to work out the rate of reaction at 45 seconds, so about there, and also at 120 seconds. Now to work out the gradient of a curve, you have to draw a tangent to the curve at that particular point and then work out the gradient of the straight line. So I've drawn a tangent here at 45 seconds, and it follows the curve pretty well because the curve is almost straight here. Now what we have to do is work out the gradient of the tangent, and to do that we need to draw a triangle like this. And the gradient of the graph is given by the change in y's, the change in the y-axis, divided by the change in the x-axis. So let's just work that out now. So if I do 40 divided by 66, what I get is 0.606. Now, the units of that is going to be centimetres cubed per second. And that is the rate of reaction at 45 seconds, achieved by drawing a tangent at the curve and then calculating the gradient of the straight line that you've drawn. Now remember, of course, the rate of reaction is always going to be greatest at the start, because that's when the concentration of the acid is going to be at its highest, there are more particles per unit volume, and therefore more collisions per unit time. So if we move on to 120 seconds, let me draw the triangle and work out the gradient of this straight line. So nice and straightforward, this one. So change in y over change in x. So 50 divided by 180, and we get, put that in my calculator, 0.278, and the unit centimetres cubed per second there. And of course, as we might expect, we've got a much lower rate of reaction than we had at 45 seconds. And of course, after about 180 seconds here, the reaction's over, so the hydrochloric acid has run out. Draw a tangent, of course, the gradient's 0, so the rate of reaction is 0 centimetres cubed per second. So let's have a look at the same reaction here. And what we're going to do, we're going to alter things like the size of the calcium carbonate chips, the temperature, the volume, and the concentration of the acid. And in each of these examples, the calcium carbonate chips are going to be in excess, so that means there's more than enough calcium carbonate to react with all the acid in each situation. So I've plotted for you an example for A. So we've got medium-sized calcium carbonate chips, a temperature of 20 degrees, 50 centimetres cubed of acid, and the concentration is X. Now if we look at B, what's changed? Well, the calcium carbonate chip's the same size, temperature's the same, volume of acid's the same, but the concentration of acid is double the concentration in B. So that's going to do two things. Firstly, It's going to increase the rate of reaction. And because the concentration's double but the volume's the same, we've got twice the number of moles of acid. So we're going to get exactly twice the volume of carbon dioxide. So let me draw the graph for you. So an examiner marking this is going to be looking for two things. Firstly, the gradient of the graph is steeper. And secondly, we get exactly double the volume of carbon dioxide gas produced because we've got twice the number of moles of hydrochloric acid in this case. So let's have a look at C. Now, how is C different from A? Well, the size of the calcium carbonate chips is the same, the temperature's increased, but the volume and the concentration of the acid is the same as A. So what's going to happen is the rate of reaction is going to increase. However, we will get exactly the same volume of carbon dioxide produced. So let me draw that for you. So of course, looking for two things here. One, steeper gradient of the graph. Two, exactly the same volume of carbon dioxide gas produced. Let's look at D this time. So how's D different from A? Well, we've got small calcium carbonate chips this time. Everything else is the same. So a greater surface area of the calcium carbonate. Remember, same mass but greater surface area, greater rate of reaction. So let's draw what the graph would look like. So once again, steeper gradient but exactly the same volume of carbon dioxide gas being produced. So let's compare A and E. So we've got the same size of calcium carbonate chips, same temperature. However, we've got double the volume of acid, but it's half the concentration. That means we've got the same number of moles of acid, so we're going to get the same volume of carbon dioxide. However, because the acid is more dilute, we'll have a lower rate of reaction, so therefore the gradient of the graph will be less steep. Let me draw that in for you now. So we'll be looking for two things there. A less steep gradient, but exactly the same volume of carbon dioxide produced. So finally, let's compare A and F. So what's changed here? So the size of the calcium carbonate chips is the same, temperature is the same. However, we've got double the volume of the acid. It's the same concentration. Therefore, we've got double the number of moles of acid. Therefore, we're going to get twice the volume of carbon dioxide produced. The concentration is the same. Therefore, the rate of reaction and therefore the gradient is going to be about the same. Let me draw the graph in for you. That's what we're going to be looking for. So pretty much the same gradient, certainly at the start, double the volume of carbon dioxide being produced. So looking at the same reaction again, notice I've not connected the conical flask to a gas syringe this time. What we could do is we could measure a certain volume of hydrochloric acid and add the same mass of calcium carbonate with exactly the same surface area. But what we could do is we could repeat the reaction with a few different concentrations of hydrochloric acid. So all we could do this time, if the calcium carbonate's in excess, we could time how long it takes for the bubbles of carbon dioxide to stop. Now, to convert a time to a rate, remember you do the following. You do number 1 divided by the time in seconds, and you could multiply that by 1,000. That just makes the numbers on your graph a lot easier to plot. Now, you would probably end up with a graph that looks like this. So we've got concentration on the x-axis and we've got rate of reaction on the y-axis. Note the units of rate of reaction are seconds to the power of -1 multiplied by 1,000. Now let's have a look at the rate of reaction at different concentrations. So what we can see here is when the concentration is 1 mole per dm cubed, the rate of reaction is 10. 2 moles per dm cubed, the rate of reaction is doubled, it's 20. And if we double the concentration again to 4, the rate of reaction is once again doubled to 40. Now in this case, the rate of reaction is directly proportional to the concentration. And the reason for this is if you double the concentration, you double the number of particles per unit volume, and therefore you double the number of collisions per unit time. Now, a lot of chemical reactions will work like this, not all of them by any stretch of the imagination, and more about that when you come to A-level. Okay, so that's the final video in the rates of reaction series, rates and graphs, hopefully made simple. Thanks for watching.